All right, so CAM kinase seems to be coding the duration of your exercise. So there's frequency, intensity, and duration to cause adaptation. So what's coding the intensity component of the exercise? And so for the intensity component of the exercise, then we look to this protein kinase called the AMP activated protein kinase. Okay, and so AMP activated protein kinase is a heterotrimer. So remember, CAM kinase is an oligohexamer, which means that it's 6 subunits, but they're all the same. AMP kinase is a trimer, but it's a heterotrimer. And the hetero means that there's 3 different components that come together. The first component is the alpha component. That's got the catalytic activity. That's where the phosphorylation events are mediated. So that's the enzyme activity is in the alpha subunit. Everything else is going to be regulatory. Alpha subunit also has this phosphorylation site at 172, and that's going to regulate the activity of the kinase, and the kinase activity again is in the alpha subunit. The beta subunit is a scaffolding protein, and it holds together the gamma and the alpha together as well as the beta, and it's now going to localize it within the cell. And what beta does is it binds the subunits together, and then it also binds to glycogen because it has a glycogen binding domain. So that should tell you if you have less glycogen, you can get greater activation of AMP kinase. So one way to activate AMP kinase is to deplete glycogen, because the beta subunit glycogen binding domain, when it's not in contact with glycogen, you have higher activity of AMP kinase. The gamma subunit of AMP kinase is the nucleotide binding domain. And what that means is it can bind either AMP, ADP, or ATP. When the gamma subunit, and it binds to 2 of them, one on either side, you can see the tail on the far side. So it's binding to 2 ATPs, AMPs, or ADPs. When it's bound to AMP or ADP, AMP kinase isn't as accessible to dephosphorylation. So you don't have the accessibility for the phosphatases that would normally take this off. So you're regulating both the phosphorylation of AMP kinase, but what the AMP is doing is it's regulating dephosphorylation. AMP, when it's bound to AMP, it prevents dephosphorylation. Okay? And when it's active, AMP kinase is a serine-threonine protein kinase, just like CAM kinase is a serine-threonine protein kinase. All right, so how does this work? Well, if we look at a target protein like ACC, and we give radioactive ATP, when you add ACC together with AMP kinase, what you can see is AMP kinase phosphorylates. It transfers the radioactive phosphate group from ATP onto ACC. All right, so it's a kinase. That's basically what it does. And when you add either AMP or ADP together with the AMP kinase, now what happens is the activity goes up. So AMP in the presence of AMP kinase will increase the activity of this protein by 3-fold. Okay, so AMP kinase is an active protein, but its activity is massively upregulated in the presence of AMP or ADP. So the question is, why is that? Well, what happens when you have AMP and AMP kinase, AMP and AMP kinase is that AMP kinase becomes phosphorylated. You can see that here when you have the kinase that phosphorylates AMP kinase. So in this case, we'll just call it AMP kinase. Together with AMP, now you get phosphorylation of, this is AMP kinase, P63 is AMP kinase. And then when you have calcium at high levels, it is somewhat inhibitory, but when your calcium is lower, now you've got a bigger effect here where you can see greater phosphorylation and a little bit higher activity. But it's really that what's happening here is that when AMP kinase is bound to AMP, it becomes more phosphorylated. And really what we're seeing is, I think that in fact what this was no AMP here, but with calcium calmodulin kinase, and this is AMP together with AMP kinase. Now you got greater activity. Okay, so really what we're seeing is we get AMP kinase becomes phosphorylated. If phosphorylated at this site, threonine 172, and when it's phosphorylated at that site, its activity is higher. Very similar to CAM kinase, that becomes autophosphorylated. And when it's autophosphorylated, does that do? It means that even though calcium goes away, the calcium signal stays around for longer. So now AMP kinase is going to be activated by AMP, and the longer that AMP is there, the more AMP kinase activity you have. But because the phosphorylation is there, it's going to again go away relatively quickly. But because it's phosphorylated, it's not as quickly as we regenerate or take the AMP and regenerate it into ATP. So what the phosphorylation does is it elongates or lengthens the length of the signaling cascade. So what happens here is to generate AMP or ADP, basically what we're doing is ATP is being used during exercise when we're contracting our muscles, especially when we contract our muscles like motors, where we're using lots of cross-bridge cycling. We're using a ton of ATP. If we need to regenerate the ATP super fast, because we're going at a high intensity, we're going to combine two ADPs together through the myokinase reaction to produce ATP and AMP. So the faster we use ATP and the faster we need ATP, the more AMP we're going to generate. So that should say that if we go high intensity exercise, we should increase AMP kinase activity more. And in fact, that's what you see. Low intensity exercise increases AMP kinase activity, but high intensity exercise has a much greater effect on AMP kinase activity. So now what we've got is a calcium calmodulin kinase, which is coding the duration of the exercise bout. And now we've got AMP kinase, which can code the intensity of the exercise bout. So when we're doing high intensity work, we're going to get AMP kinase activity. When we're doing lower intensity work, we're going to get calcium calmodulin kinase activity. So how do we modulate this? Well, the first thing we can do is if I work out in a glycogen depleted state, I'm going to get greater AMP kinase activity. All right, and so this is by Greg Steinberg, and what you see here is the alpha-1 and alpha-2 AMP kinase. And these are just two flavors of the AMP kinase. And what you can see is when you do exercise, the exercise doesn't affect alpha-1 AMP kinase, doesn't turn on alpha-1. It turns on alpha-2. And if you start with lots of glycogen, it turns it on a little bit, but in this case, not significantly. But when you start in a low glycogen state, now when you exercise, you actually get a greater and a significantly greater increase in AMP kinase activity. And if you look, the activity is measured by looking at phosphorylation of ACC. Here you see, even though you don't see a statistical increase here, its downstream target, because of amplification, you see a significant increase in ACC phosphorylation. But that increase is almost doubled by starting your exercise in a low glycogen state. So now, because of that glycogen binding domain, which is keeping AMP kinase activity lower, when you start with a low glycogen in a low glycogen state, now low glycogen is allowing more AMP kinase to become activated, and that higher AMP kinase activity is translated into a greater response. Again, one of the things that's important is to remember that alpha-1 AMP kinase not really changed by the activity of exercise. Alpha-2 AMP kinase turns on really well immediately after exercise, and then just like CAM kinase, and unlike mTOR, which is on for 18 hours, AMP kinase is off already by 3 hours later. And if we were to look at 30 minutes later, it would have already been down 50 to 75%. Okay, so it's rapidly turned off. Both calcium calmodulin kinase and AMP kinase are rapidly turned off. So with AMP kinase is a trimer. It's a heterotrimer. The kinase activity is in the alpha subunit. The alpha subunit or the kinase activity is regulated by AMP binding. So when AMP is bound to the kinase, its activity goes up threefold. And by phosphorylation, which activates it again by another twofold. It's also inhibited by glycogen binding. So when you have more glycogen and you've bound your AMP kinase into glycogen, you don't get as much AMP kinase activity. So a simple way that you can accentuate the effects of high intensity exercise are to do it in a low glycogen state. AMP kinase is activated by the rise in AMP that happens at the beginning of exercise or during really high intensity work when we're using ATP faster than we can regenerate it. And endurance exercise increases AMP kinase activity proportion to the intensity. So AMP kinase is really the alpha 2 subunit is coding the intensity of your exercise. So now when we talk about frequency, intensity, and duration, we're actually talking about specific kinases. Frequency, we haven't really talked about that. Intensity, that's going to be AMP kinase. Duration, CAM kinase. So if we do a high intensity exercise, low duration, more AMP kinase, less CAM kinase. If we do a long duration, low intensity, more CAM kinase, less AMP kinase.